welcome the three teaching assistants that we have today, Vartika, Ritwik, and Devon. These are PhD students in the Curie College of Computer Sciences at Northeastern. We're very grateful for them as well. Well, so without further ado, so I see we already have questions. So let's maybe have Ryan and the TAs get started. Thank you very much.
Great, thank you very much, Olga. Certainly appreciate the opportunity to be able to present this hands-on workshop. And again, thank you to the TAs taking their Saturday mornings or afternoons, depending on where you're at. And also all the participants. We covered a lot of material yesterday. And I thank you for coming back and sticking with us. I would just say that, learning a programming language, particularly from scratch, is a challenging process. And so what I would recommend is, even if you didn't necessarily get all the ideas and concepts yesterday, take a layered approach. So maybe you can go back and review the material, maybe review some of the code and the code examples, and also layer that on top of additional learning resources. At the end of this, I will point some out. There's some great free online books that you can take, that you can read, that can, again, go through lots of this material, even more things in more detail. And so, really taking a layered approach and kind of revisiting the same concepts over and over again, I think is really useful in order to make things stick. And then you start feeling more comfortable with the language, and then you can start doing more with it. So great. For today, we are going to cover a fewer number of topics. We're going to start out by taking a look at the example exercises that we had discussed at the end of yesterday. The idea of those exercises was to give some questions in practice about some of the main ideas that we covered yesterday. So I'll go through those. I'll go through those solutions. Those solutions will also be posted online, so you can refer to them after the course if you want to go back and run that code for yourself and play around with them and make some maybe modifications to that code. Then we'll get into the new topics for today. Really, we're just going to cover two main topics. The first is the idea and concept of tidy data and what it is. Tidy data is really important in the R ecosystem right now, particularly in some of the more modern ways in which people are using R to do data analysis. So we'll talk about tidy data, and then we're going to shift into a somewhat large topic, but I think a really important topic. It's the idea of the tidyverse, which is a collection of R packages that revolve around the idea of tidy data. And then we're going to look at a particular package called dplyr that allows you to do some really powerful data manipulation operations and data analysis. We're going to learn some new syntax. It's going to look a little strange at first, but I think if you practice with it, you'll really appreciate the power of the kinds of data analysis you can do using this dplyr R package. Great. Let me orient you to some materials, particularly if you weren't able to join us yesterday. The first thing I'd like you to do, if you haven't done it already, is please visit the second day materials on the May Institute website. If you go there, there are some setup materials. I hope at this point you have a working version of R and RStudio that you can use to go through the examples and be able to do some of the practice materials. I have some set up here if you haven't done that yet. And in particular, at this point, if you haven't been able to install R or RStudio, go to this document and look at the RStudio Cloud section here. What I've done is I've set up a workspace that has all of the data and the exercises and the files ready to go. I've installed the packages there. So it's really a two-step process. You first need to register for a free RStudio Cloud account. Once you do that, then click this link here for the workspace. If you do that, let me just show you in real time what that looks like. If you do that, this will take you to a page here that will essentially have the exercises for the course that we're going to be covering. If you click on the exercise link and you give it a few seconds as a cloud machine computer is being brought online for you, it's going to start up an RStudio workspace that has all the data that we're going to be working with and also the exercise files. Let me just do that. It should take just a second as it spins up, and it'll look maybe a little bit different when you boot it up. But in any case, you will be able to see a running version of RStudio all ready to go with the files that you need to do the exercises. All right. So that's probably the fastest way to get started right now if you haven't yet gotten R or the data files set up for the workshop here.
Right, and there was a question that may be good to mention to everyone again.
Please, yeah.
Could you say this again, if the exercises, like the solutions to the exercises, will be posted?
Yes, thank you. Yeah, so Olga, I'll post those on the May Institute Google Drive there, so we have them associated with the courses. And also right now, the answers are already up there. So if you go to the GitHub repository, and again, those are linked in the documents here on the May Institute website. If you go to the GitHub repository, that will take you to this page. This has all of the materials there, including the lecture slides. If you haven't gotten those yet for day 2, you can grab those by going to the lecture slides folder. You can click on the day 2 PDF and you can click download, for example. If you come back here to the GitHub repository, let's see where we're looking for the exercises. They are located here, and the solutions actually are already posted. So we're going to do some day 2 exercises. Don't look at those solutions yet. I would like you to maybe try these exercises first before you look at the solutions, but the solutions are here as the R file. So if you look at those, you have all the code here that talks about the solutions to those. So you can review that again on your own time after the course, but we're going to go through those live now. Okay, great. Any other questions on logistics? If not, I am going to bring up RStudio. I have changed the theme, by the way, of RStudio here. I'm hoping this might be a little easier to read. Sometimes the light background is a little bit difficult to see. So I've changed the background. And just if you're interested, if you go to Tools, Global Options, and go to Appearance, there's all kinds of different themes you can use. Some people like dark themes, some people like light themes. There's all kinds of ones you can use depending upon what you like. So I'm going to use a dark theme here to make maybe the code a little bit easier to read. Okay, so let's look at the first set of exercises. This is the first steps with R exercises. The idea here was to practice the concepts like variable assignment, working with vectors, and writing conditional expressions. That's what we covered as one of the main topics yesterday. So let's go through some of these answers. I'll sort of walk through the answers, and if anybody has questions, please ask them in the chat and we can address them here. So the idea here was we have some hypothetical LCMS experiment, and we're using a 60-minute gradient here. The first question here was to create a variable called gradient underscore min to hold the length of the gradient in minutes. So this was just simple variable assignment. We learned about naming variables here. We learned about this assignment operator that looks like an arrow sign, and we can put essentially the value on the right-hand side gets assigned to this variable. And so if we remember in our editor, if we hit Command Return, that will execute the code in the console down here. Okay, you can also put your cursor on the line and click the Run button. It will do the same thing. But if we look down here in the console, if we type gradient min and hit return, we can see that it is in fact 60. So this was a simple variable assignment. Next, the question was to convert this gradient length, which is presumably in minutes, because that's what we said, to seconds. So the concept here is we're going to take a variable and we're going to do some math on it. So if we want to convert minutes to seconds, we just need to multiply by 60. And so now we have a new expression here that we're going to assign to a new variable called gradient seconds. Let's execute that. And you probably also noticed over here in the environment, we can see these variables also popping up in their values. So that's a nice way to see what's called your R workspace, what the variables that your R environment knows about. In this next question here, the idea was that, let's say we ran some additional experiments. One was 15 minutes and the other was 30. And now we want to hold all three of these experiments in a single data structure. The structure we want to use is called a vector. So we learned about vectors yesterday, and we also learned about the C function. C stands for combine. And so we use the name of the function, which is C, in an open parentheses, and then we can just put the different gradient lengths here, 15, 30, and 60 inside of the function with commas between them, and that will wrap all of these values up in one little nice package for us. We'll assign that to a new variable called gradients. We're using an S now to say that there's more than one. So let's execute that expression. So again, this thing is a vector here, and we can see its contents over here in the environment. It has three values here, 15, 30, and 60. So just like we were able to do math on a single value, we can also do math on multiple values. That's a cool thing about working with vectors. So if we want to convert all of these to seconds, we actually use the same exact expression we used above for the single value, but now we can just use the vector instead of the single value, and we get back a new vector here where we've multiplied 60 by each element in the vector. So we've just done essentially three computations in one line of code, which is a pretty cool thing to do.
Hey, Ryan.
Yes.
Some people are having trouble reading your coding theme.
I'm sorry. Okay, thank you. I appreciate it, Devin. Apologies to everybody. Let me go back to the light theme and let's maybe I should do a poll to see if people like the light theme better. And maybe TAs, is that easier to read? I'm sorry. my old eyes have perhaps adjusted to these dark themes. So apologies for everybody. Hopefully this is better. Just go with the defaults. That's always the best way to go. Okay, and just to guide you in here, these comment lines have the hash in there, and the questions are in green there. This is not the R code. This is just the free-form comment code here that would not get executed. Okay, great. So again, the idea here is we can do math on a whole bunch of values in one little expression by using vectors. Okay, and so let's look at gradients plural sec. Let me pull this up here, and we can see that now we have three values. We did math on all three of those values. Okay, so we're getting maybe a little bit slightly more interesting here. I gave to you a vector here that I defined. These had a bunch of mass over charge values here. So we're going to execute this code to get this vector in our workspace. And then the question was, how many values are there? Okay, you could obviously go and count by hand, but I don't suggest doing that. That's what computers are for. One way we can do that is with the length function. We can ask, what is the length of this vector? So let's just type that out, length Greek mz, and then that will tell us that there are actually 10 elements in this vector. Okay, so we don't have to count. We can just use this nice function. It can tell us, and we can assign that also to a variable. We have some other functions here we can use. What's the minimum m over z? Well, there's a nice function called min and max. We reviewed some of these functions yesterday that we have access to, and it's the same kind of syntax. You use the name of the function and open parentheses and then the vector, and it will spit back out the minimum and maximum values. So we can just print those out or execute that code. And for example, the max m over z value is 1041 and change. Okay, so that's the idea of working with vectors. And the idea is that we can do math operations on those vectors just like we do on single values. And also, let's do another one here. Like if we wanted to compute the mean of the m over z values, we can use the mean function to do that. Or the standard deviation of that value, those functions are there for you to use. I mentioned R has thousands and thousands of functions across built-in and also across different packages. One question is, how do I find out about what's available to me in R? Sort of what can I do? What functions are already defined? Google is usually a good place to do that, where you can search for R. And then sometimes you need to put programming language because R is such a bad term to search for in Google because it's so generic. But you can put like R programming language and then the task you're trying to accomplish. And usually you'll have some pretty good results about getting information about functions that might be available to you. Okay, let's talk about conditional expressions. This is actually a really important concept and idea that you use all the time in data analysis. Again, conditional expressions allow you to ask questions about your data. These are in the form of yes, no questions, okay? And you might remember that these conditional expressions return true and false values. So in this particular question, we wanted to write a conditional expression to find the m over z values from this vector up here that we already worked with that are less than 600. Okay, and then a couple things. What does this expression return and what's there? So let's actually run this code. We just take the vector name, the variable name, we use the less than operator and then put 600 on the left side. Let's run this code. Okay, and so also let me print out this vector for reference here. So again, we had all of these m over z values. And what this expression did was ask this question about each value in our vector. It said, 968, are you less than 600? The answer to that is no. So we got a false return there. Then it asked that same question about 812, are you less than 600? The answer is no. So essentially ask this question over and over again for all of the values in our vector. So we're doing lots of computations here, lots of question asking in just one little short line of code, which is really cool and really convenient. Looks like there are some, so 500 and 400, these values are trues. So and 300 here, so we can see some trues are also coming out of this vector, this conditional expression. Notice that this expression did not return the actual numeric values that are less than 600. This expression returned a list of a vector of true and false values. Okay, so it asked the question for each value here in the vector. If we wanted to actually get the numerical values that are less than 600, we have to use this subsetting operation that we talked about where we use the square brackets. Notice that this expression here has just been copied and placed inside of the square brackets here. Okay, and we have to reference that with the vector in front. So we're saying take this vector and now subset it. That's what the square brackets mean. And then we have to place inside the conditional expression that we want to subset by. Okay, we put that inside here. Now if we execute this, we only get the values out that are less than 600. And in fact, we can see down here from these results that the values are less than 600. Okay, so an important distinction between the conditional expression and the slight modification where we actually get the values that the conditional expression satisfies. Okay, so that's a little complex. I would recommend, if this is still a little bit challenging to think about, to play around with some different examples of conditional expressions and the subsetting, change this to greater than or not equal to then, and look at the outputs. And I think you'll get comfortable eventually about what this is and what it can do. We're going to combine this in a couple ways here. So another example, consider we have some charge states for some of the ions that we're looking at. Let's write a conditional expression that find these charge states that are equal to 2. So an important thing here, and you have to be careful about, is we talked about the difference between the single equal sign and the double equal sign. Turns out that the single equal sign will actually do variable assignment, just like this arrow operator that we learned about and used. You can also use a single equal sign to do variable assignment. That's not what we want here. We want to ask a question about which values are equal to 2. You need to use double equal signs to do that. Okay, let's execute that. Again, we get another set of true and false values. And if we want to get these precursor m over z values that are, let me show you here. We're actually going to combine the idea of we're linking these precursor charge state values up with the precursor m over z values. Okay, and so this expression is a little bit different. We're going to take our m over z values and find the mass to charge ratio values where the charge state is equal to 2. So we're using two different variables here in order to get a different type of data. So we can use this index expression that we use for the charge state of 2, but use that with another vector, the m over z values. And this will in fact give us the m over z values where we had the charge states equal to 2. Okay, so pulling out these elements of the vector. Okay, so this is combining the idea of conditional expressions with vectors in different ways to give different slices of our data. Okay, and this happens all the time. You want to slice your data maybe based on p-value, or you want to subset your data based upon a disease condition. For example, what's the average intensity value for my healthy patients versus sick patients, and so on. These are very common questions that you would want perhaps to address in your experiments, and you would use these fundamental operations that we just talked about in order to do these kinds of subsettings. Okay. Any questions here? So I would say, even if you didn't get everything exactly here, the solutions are going to be online, and I would just walk through them step by step and just pay attention to the outputs, take a look at them, maybe make some simple modifications on your own to practice working with this kind of code. Okay, and also if you have questions, write them down, and we can bring these up at the end if you want to share your screen or dig into more details. Okay, let me go over the exercises for the second set. This has lots of similar concepts that we talked about yesterday, but now we're going to apply them to the data frames, to the data tables that we talked about. So the first part is we need to load up the tidyverse packages to give us the functions that we're going to use here. You'll notice when you load the tidyverse package that you get some outputs here. There are some red X's. Don't worry about these. These are just sort of standard messages that's telling you what it's doing. Don't worry about this. This is completely normal and common, and you'll see this whenever you load up the tidyverse library. We're going to be working with a data table here for these exercises. This is some proteomics data that has measurements on proteins and peptides and fragments that were identified in a particular experiment. So let's load this up here. And we learned about this read CSV file where you use this function along with the name of a file to load it up. I've also added this additional piece of the function here. It's called guess max. This just helps the read CSV function read the data file in because there's so many rows. This has over 1 million rows in it. So it's a pretty big data file. And this guess max essentially tries to guess the types of the data in the file in the first 10,000 rows. So don't worry about the details too much, but I just wanted to point out this is a little helper for this particular file because it's so big. It helps the CSV function read the data. So let's run this code here. Okay, and it's actually a big file here, and you can see a progress bar that's popping up. It's 100 and close to 200 megabytes here. So a pretty big data frame here. I think you'll recall here that if we actually just print the data frame out, we actually get quite a bit of information here. It tells us, again, in the way it prints out, the number of rows here. So it has 1.2 million rows and 16 columns here. It gives us a preview of some of these columns along with their column names. It also tells the type of data here. So these are characters. These are alphanumeric types of data, which makes sense for things like protein names and peptide sequences. We have charge states here, which are numeric values and so on. So there's lots of information about the data frame that we can get just by printing it out. But we can also use functions on the data frame. We can use the nrow and ncol functions on this data frame to get the number of rows and columns. So let's execute those. So just like this printout told us, we have about 1.2 million rows. If we use the nrow function here, we can also get that information that way. We also have 16 columns. Again, that lines up with expectations with what we have. This dim function can also be used to get the dimensions, both of the dimensions, so the rows and the columns. This thing is actually a vector. So if you remember our vector subsetting operations, we can actually call this expression here. We could save this to okay, this, let's say call this dims maybe 1 or something. We can save this to a variable, and then we can index this using the number 1 to get the first element. So we can get the number of rows by indexing this vector, or we can use 2 to get the number of columns there. So this is vector indexing, which we talked about yesterday. You can do the same thing here. Again, we talked about data types here. So if you print out the column, or sorry, the data table, we can see the data types here. Sometimes that's important to understand what R thinks about what the data is. Here's another cool thing. I don't think we talked about this yesterday, but there's a function called view with a capital V. Okay, that's really important. A lowercase v won't work, but if you use this view function and you provide the data table and you're in RStudio, something cool happens. Let me run that. We got a new tab that just popped up here. Okay, so don't be afraid, your code is in the tab next to it, but it popped up this new tab that gives us a nice data table view here of what the data looks like. And you can actually sort in this. This is a pretty big table. So if you click these columns here, you can sort the data, although it might take a little bit of a time because it's such a big table. But you can look at your data table. You can actually use this search box to search for different kinds of things. So it's a really cool interactive way to look at your data. Okay, so you can get that anytime with any data table using the view function with a capital V. That's really useful. We also talked about this $ operator. So if you have a data table, again, remember we have a bunch of columns in the data table. If we use the variable name and the $, that allows us to access data from any one of the columns. And RStudio is nice. It will pop up this little list for us that we can use our arrow keys to come from, to use. And you can use this to select a particular column. So this question said, get the file names here from the data table. So we can scroll down here to file names and push return, and that will fill in the column name. And when we press return, that gives us back a vector of all of the column names, of all of the data inside of the file name column. Okay, there's a lot here. This is a very long a vector here. And we would expect to get one value for each row, because in the data table, we're essentially just taking one of these columns and grabbing all of that data. So if we ask for the length, so the number of file names that got returned, that is the 1.2 million, which is also the same as the number of rows in our data frame, just as we'd expect. Okay, so essentially, we pulled out all of the file names in one column using this $ operator. You'll notice there's actually probably lots of duplicates here. We might want to ask how many unique data file names do we have? We can use the unique function to do that. And we just pull out all of these values using the syntax we just described. And if we do that, we can see that we get a much smaller set of file names. And then look at this, we can actually chain this as well. We can type length in front of that function call and add inside of that all of the unique values, and this asks for the length of the unique set of file names. There are 12. So we know from this particular experiment there were 12 raw files that went into it, which we may not have known just by looking at the data table by itself. In fact, we wouldn't have known. We would have had to have run this kind of computation. Okay, let's get into something that's a little more interesting. Again, we have this big, long data table here. It has 1.2 million rows. So this question was saying, get the subset of the data table that correspond just to this protein here. Okay, and how are we going to do that? We want to use a conditional expression. Okay, just like we subsetted a vector before using a conditional expression, we're now going to subset a data table using a conditional expression. And we're going to combine this $ operation that says, get all of the values of the protein names. So that's this first column here, get all those values. Then I want you to ask the question, which of the protein names are equal to this particular protein that I provided. So let's just take this individual conditional expression, and let's execute that and see what we get. Again, we get a bunch of true and false values. In fact, most of these things are going to be false because most of the proteins aren't this particular one, but there are some trues hiding down there somewhere in the output. So in order to subset the data frame, it looks just like the vector operation, except we have to provide the rows we want to filter, provide a comma here, and then talk about the columns we want to filter to. And if we don't provide any column filtering, we just leave it blank. That says, give us back all of the columns. So this expression says, give us the data table for this particular protein. If you just say it in English, that's what this expression does. Give me the data for a given protein. So let's execute that. The output is a much smaller data table. This has 288 rows, and the protein name, it's a little truncated here in this view, but let's use that view function that we learned about on this particular expression. We can look at this data table and see that, in fact, that we have the values for this protein name. Okay, and we could scroll through the entire list and confirm that, in fact, this protein name is all that's there. Okay, so now we just got the data for a particular protein. Let's count up the number of unique peptides that we've determined for this particular protein. This is a common question you might ask about your data. Let's write the code to do that. We're going to do this in a couple steps here. Let's take that subset that we just did with the data frame and let's assign that to a variable so we can work with it. So same expression we used up here to get the subset, and we're just assigning it to a new variable name called dat_subset. So let's execute that code. Again, this is just that data table that we just looked at with 288 rows. Now let's calculate the number of unique peptides, and we're going to do that in a couple steps. We can get the peptides from this peptide sequence column. So we're going to use this $ operator to extract that data. Let's take a look at that. This gives us the peptides that only appeared in the data subset. That's what this expression says. Let's assign that to a variable called peptides. Okay. Now we can ask the question, what are the unique peptides there using the unique function? So peptides here, let's take a look at it. Looks like there are lots of duplicates here. We identified the peptide through a variety of ways here. Let's get the list of the unique peptides so we can use the unique function and assign that to a variable called unique peptides. Oops, let me type that right, unique peptides. So now this is a much smaller list, and you can look at it and see that we should not have duplicates here, and we don't. Then we can use the length function on the unique peptides to determine that for this particular protein, we detected 7 unique peptides. Okay, so there's all kinds of ways you could write this code where we make it maybe a little more concise. And so here's another way you can do it. You could get the peptide sequences directly. Then we can ask for the unique set of those peptide sequences. Then we can get the length of those. And so we could do this all in one expression like that, where essentially we combine multiple steps here into one seamless expression. In fact, you could also rewrite it in some complex code starting all the way from the original data frame, but I won't show that now. Okay, so I think, so the idea here is that we learned a bunch of building blocks yesterday, and the building blocks may seem a little simple or mundane, but in fact, the idea here is that you can use a bunch of these individual pieces to start building up these kinds of expressions to start asking some interesting questions about your data, okay? Like the number of peptides you identified per protein, okay? All right, so those are the solutions. Like I said, those solutions are on the GitHub website here. If you go to the main page and go to exercises, the exercises without the solution have the exercises in their name, and the solutions surprisingly have solutions in their name. So you can go through and take a look at those, run through those again, and play around with some of those code examples to help maybe give you some more insight about what's going on and give you some more practice. All right. Okay. TAs, any questions come up that would be useful to address to the larger audience?
I don't think so, Ryan. I think everything's
Okay.
pretty good.
Okay, great. All right. Okay, so those are the solutions. Let me now switch back to the material for today. And sorry, anybody have any other general questions from yesterday? Happy to maybe talk about those before we head into the material. Okay, like I said, we can also at the end of the workshop here, we can have people stick around and you can share your screen if you'd like, and we can dig into some more details. Okay. As I mentioned today, we're really just going to cover two topics. So we're not going to cover as many sort of ideas and concepts as we did yesterday. But one of the topics here, particularly on using the dplyr pipeline in the tidyverse, is going to be lots of hopefully really useful ideas and concepts that we can use, or you can eventually use when you go back to your own job or back to the lab that you work with, and maybe start doing some data analysis with data that you're actually generating. Before we talk about that, I just wanted to spend a little bit of time talking about the concept of tidy data, because this is really important for modern R, doing data analysis with R sort of in a modern way. So the goal of this module, we want to talk about tidy data, how it differs from messy data, and how to recognize messy data, why messy data is hard to work with. And then we'll touch a little bit about what the tidyverse is, and I'll point you to some interesting packages that we aren't necessarily going to cover in this course, but are going to be really useful, I think, to learn. And you'll probably work with these packages in the future as you continue to learn R. Okay, so we're going to talk about the idea of messy and tidy data. Okay, but before I do that, I just want to be careful about what I mean by these terms. When I talk about messy, I don't mean that in the negative sense. Okay, messy data isn't necessarily bad data, and tidy data isn't necessarily good data, sort of in the absolute sense. The idea here is that when we do data analysis, we want to make sure that we have our data in a format that's ready to go. Data that's ready for data analysis, that doesn't have strange features or formatting or other issues that would make the data analysis process more difficult than it needs to be, or perhaps even cause problems for data analysis. So that's what's meant about tidy data, data that's essentially ready to be used for analysis. And we can contrast that with messy data that is conversely essentially data that's not ready to be worked with yet. We need to do something to that data to get it into a format that's easier for us to work with. So again, please don't think of messy as being necessarily a bad thing. It's just noting that the data is not ready for analysis. Okay. When we talk about tidy data, one of the main figures in the R community is a person named Hadley Wickham. You may have heard about him if you've encountered R in any way. He's written a ton of packages, including the ggplot2 package for visualization. He's the main architect of the tidyverse and the dplyr package that we're going to be talking about. And he likes to give this metaphor about data, sort of this quote by Leo Tolstoy about the idea that in his writing, he talked about in one of his books that happy families are all alike, but that unhappy families are all uniquely different in how they're unhappy. Okay. And how does that relate to data? Well, that applies to data as well. And the general idea is that tidy data sets all look alike in their format. Okay. They have a certain structure that exists, that is sort of understandable, that you can look at and understand the data more easily versus a messy data set. The problem with messy data sets is that they all can be messy in their own unique, unusual ways. Okay, and that's really challenging to work with because if you have a data set that's messy, has strange formatting, has weird aspects to it, it's difficult to reason about what it is and what it's trying to do, and that's a problem. The idea is that we want consistency. We want tidy data sets before we start doing analysis. Okay, so that's the fundamental idea. As you probably know, messy data is all over the place. You know, when in classes, classroom situations and so on, oftentimes you're giving example data sets that are nice and well formatted, and that's fine. That's great to start with. But when you start working with real world data, maybe data you find off the internet, maybe you find data from other sources, maybe colleagues are giving you data that they've generated in their own maybe labs or whatever, and that data can also be messy. And what we want to do is we want to go from this messy data to tidy data. That's the main idea. And sort of one of the dirty secrets, if you will, in sort of the data science, data analysis field is that oftentimes we spend something like 90% of our time just working with the format of messy data. And we only really spend about 10% of our time doing something useful or interesting, like with the data, like doing data analysis or maybe doing machine learning. So this, dealing with messy data is really sort of an important part of sort of your tool belt as you work with data, as you get more experience working with data. Okay, data can be messy in all kinds of ways here. So Excel spreadsheets are an example of where you often get messy data. It's something that we often work with. And this was just a little example of some hypothetical teacher who is maybe grading her students. And this data is messy in the sense that we don't have a nice defined table here. There are some header rows here that we have a bunch of information here, but some header rows here. So this information is separate from the main data table here. This particular teacher is using some formatting here to indicate something. So they're using like red coloring on the text to note some certain scores, but we really can't access that information from our data. Also, these are ratios here. Ideally, these would probably represent, say, like percentage values that a person had scored on a particular quiz, but these have been written in a text form where they've written as a textual ratio. So that data is not really useful or accessible. So there's lots of ways in which this data table is messy. This data table is not ready for analysis. We'd have to do some work in order to get it ready for doing data analysis. And you probably see these kinds of examples all the time. I would say to a certain extent, proprietary MS data formats are messy in the sense that sometimes they're locked in sort of their proprietary formats, and we can't necessarily read those directly into R. So that's another version of messy. You also see lots of other examples, and also be on the lookout for badly formatted text files. This is a CSV file here, but the number of values in each column is not the same. So it looks like we have 5 values here in the front, but we only have 3 values down here. This can cause problems if you try to read this data into R, and these things happen, unfortunately, not necessarily all the time, but they're not uncommon to have these kinds of problems. So be on the lookout for messy data when you do data analysis. And sort of a main idea here is that messy data is just hard to work with. Okay, we want to try to get data that's more easy to work with. So I won't go through much there. It's important to note that just because you have messy data doesn't mean that the data itself, the quality or the integrity of the data is bad. Okay, a lot of times it's just in a format that's not ready to go. However, if data is really messy, that could be a sign of lurking data problems. For example, if somebody had to hand enter data into a spreadsheet and the spreadsheet was in a complex format, it's really easy to make data entry errors as people enter data into say a spreadsheet or something. So they could be lurking problems. So you have to pull out your magnifying glass and put on your inspector hat and just be careful. It's worth reviewing data in detail if the format is really unusual or it looks like it's challenging or complex. Okay, let's talk about what it means to be tidy data, very specifically in the R ecosystem. Tidy data, that term is used quite a bit, and it has a specific meaning. And in R, there are these 3 conditions that need to be satisfied for you to have a tidy data table. So the first idea is that all of the variables, these are the things you are measuring about a particular thing, go in columns. Okay, so in this case, I think this example data table has to do with measuring, I think, cases of diseases that occur in different countries. And so in this case, we're measuring, for example, the country name, the year in which the measurement was made, the number of cases, and the population. So these are known as our variables. These are the actual things that we're measuring. Okay, Okay, those go into our columns. The things that we're making observations on go in the rows. So each row corresponds to an observation. And in this table, you'd think about maybe the observations are, we're making measurement on a country in a particular year, and we're observing the number of diseases, cases that appeared in a particular country on a given year. That's the observation unit that we're making measurements on. And then the last idea is that each individual piece of data needs to go into its own cell. So we're not combining multiple pieces of data in one cell. Each individual piece of data that we want to analyze goes in its own cell. Okay, so that those are the 3 rules for tidy data. And if you have a data table that looks like that, then you are conforming to the tidy data principles. And this data frame, this data table is in a form that is ready for data analysis. I'm linking to a little a paper or a chapter on a book here. I'll talk about this in the resources at the end, this great book called R for Data Science. There's a chapter on tidy data where these concepts are described in more detail. It's a great resource. I'll show you that book here at the end of the day here today. Let's take a look at this data table that we've been working with. Okay, we worked with this data table yesterday. We had a bunch of rows corresponding to mass spec experiments and some data about the different experiments that we did. This is an example of a tidy data table. And whenever you have a data table, you should ask, I think, these 3 fundamental questions, or at least these 3 fundamental questions. The first is, what is the data table about? Okay, somebody took the time to put this data together into, say, a CSV file. You should ask the question, why did they do that? What is this table about? In this case, just looking at the data, we can probably infer these are raw files. So if you have some mass spec experience, you probably know that these are probably raw files from mass spec experiments. And it looks like we're linking up additional annotations about these different experiments. Specifically, it looks like there were some maybe conditions for a sample that was measured here. And it looks like we did some replication of those experiments as well. And that's listed in this bioreplicate column. Okay, so this is about a set of mass spec experiments. So that's what we know what the topic is about. Each row represents measurements that we made about a particular experiment. So for example, the name of the raw file and these other 2 columns. And then what are being measured? We know that we're measuring file names, we're measuring conditions and bioreplicates. So good to have a good idea about what your data is before you start analyzing it, so you know how and what kinds of questions you can ask. Before we talk a little bit more about tidy data, just a few notes that tidy data is not the only way. We can't always fit data into a nice rectangular structure. Okay, so if that doesn't work for your data, don't try to fit data into a data table if that's not how the structure of the data table works. And some examples of that might be more unstructured data, like maybe text data, like free-form text. You're trying to pull out text from books or something like that. You might have other kinds of structures that would fit better. An MZML file is another example of that, where it's actually a much more complex data structure that has sort of fits in more of a tree-based tree-based structure to capture that data more efficiently. So not all forms of data can fit into a tidy data table, but when you can do it, usually tidy data tables are the way to go. So just keep that in mind. And the idea between tidiness is not always black and white. A data table sometimes is not, you can't say that a data table is completely tidy or not. It depends on the context in which you need to address that. And we'll see an example of that in just a second here. Look out for signs for messy data. In particular, for example, if this is, you might see some cells in a data table that try to mash 2 different pieces of information together. So imagine these are values in a particular cell in Excel, in an Excel file. It looks like they tried to mash up the gender with the age, and they used the underscore here. This is not a good thing. You typically want the gender, say, information to be separate from the age. So these should go into their own columns. They should go into their own cells. There are some other ways here, look for data inconsistencies and so on. The idea is that as you get more experience working with data, and as you try to analyze messy data and your code starts failing or things start getting difficult to do, you have a sense that you might have some messy data and maybe you need to think about restructuring that. Let's take a look at this data table. We used this example before. We said, hey, this looks like it's a tidy data table. And to a certain extent it is, but there might be other ways in which we can make this data table even more tidy. Okay. You see something here that we might want to further tidy in this data table? Let's take a look at this run column here. We actually, if you look at this, there's actually quite a bit of data. They're separated by these underscores here. So for example, this string here looks like a date, looks like a month, a day, and a year here. We may actually want this date. This date may be important for the analysis we want to run. So it might be more useful to actually have this piece of data pulled out into its own column called date. Okay. Looks like we also have sample numbers. We might want to pull that out, and this prefix here might have some importance as well. So we might actually want to take this run column and tidy it even further to pull these pieces of data out to their own columns. Okay, so that's again, tidy data isn't always a yes or no kind of question. It depends on the context. If you just care about the raw file names, then there's no reason to spend the additional effort to pull this additional data out because we already have that data here. Okay, so it just depends on the context and how much effort you want to go to make the data as tidy as possible. Okay, so that was an idea about tidy data. That was really just sort of motivating what tidy data is and why it's important. Any questions about that, thoughts about tidy data? Okay, if not, and we'll get into some now examples here in the next section here about using this really cool dplyr package, which is going to operate on tidy data to do some interesting things here. Before I do that, I want to introduce to you the tidyverse. Okay, if you work with R and you Google for R or read about R, you'll undoubtedly come across this term called the tidyverse. And the tidyverse is essentially an ecosystem of individual R packages that all operate on the assumption that you're using tidy data. So the idea is that once you have a tidy data table that we just talked about, that now we can use all kinds of cool and interesting tools to do data analysis with them on. And these packages, there's lots of packages here, sort of the universe of all of these packages are collectively known as the tidyverse. Okay, and there's all kinds of ideas about the tidyverse, and it's constantly being expanded. So for example, ggplot2 is a fundamental package of the tidyverse. This is a data visualization package. We're not going to cover that here in this workshop, but it's certainly worth spending time to learn about ggplot2. There are some great online resources to learn about it. I think maybe at some of the other courses here throughout the May Institute next week, they'll probably be using ggplot2 to visualize some data. It's a really great package in the tidyverse and is really interesting and worth learning. Lots of other packages, for example, reading in data, tidy data, we use this readr package. There's a whole package called tidyr that it's very, lots there to dig into, but there are functions there that help you convert messy data to tidy data. That's a whole topic. You could spend a whole day just talking about that topic. But again, really some useful functions here to help make messy data into tidy data. Other functions as well. If you're interested in machine learning, there's a whole ecosystem of packages known as tidy models that take this concept of the tidyverse and allows you to do some really cool and powerful machine learning workflows using this tidy data concept. So that's something to dig into if you're interested in. There's a whole ecosystem on text mining if you're interested in doing like language processing and working with language data and trying to understand topics and information from text data. There's a whole list of packages around tidy text modeling, which is really cool as well. Okay, so just putting that out there as there's a bunch of things here that are really cool for doing data analysis with tidy data sets. We're going to focus very specifically on this dplyr package here in the next section here. It'll allow us to do really cool data analysis pipelines And hopefully using sort of the ideas here, you'll be able to go back to your classes or your lab or whatever and start doing some really cool data analysis in R using dplyr. Okay, so just to recap here, I think we went over this, but essentially just talking about the main ideas of tidy data. We have some requirements for what those are. Be on the lookout for messy data. It's everywhere. Just be aware of it, and you might have to deal with it in certain ways in order to get tidy data. And then the tidyverse is a really cool set of packages, and we're going to talk about that in just a minute with the dplyr package. Okay, so that was more sort of lecture sort of material, setting up the idea of tidy data. Let's see here, it's 9 o'clock or 9, 10, 11, 12, what, 12 East Coast time. Let's take a 5-minute break to maybe let people take a bio break, maybe refill their coffee, and then we'll get into sort of the main topic for today, which is working with dplyr. So let's come back at 9:05. And we can reconvene then and start talking about the dplyr package. I'll stick around here if we want to, if anybody wants to ask questions. But we'll come back at, sorry, 9:05 Pacific, 12:05 Eastern, and sorry, you'll need to convert if you're in different time zones. So great, thank you.
Hey, Ryan, I don't know if we have time, but I think the question that Christopher's asking might be good to go over with everyone.
That's
He's
great.
basically, yeah, asking how to separate that column with like the age and the
Yeah.
name.
That's great.
Yeah.
Thank you. Yeah, I will. That's a great example. All right, it's about 9:05. I'm going to launch a poll here, see if people are back and ready to continue. Give it maybe another minute, 30 seconds here. All right. All right, let's get back to it. There was a great question asking about, in particular, we looked at an example. Let me bring it up here. For example, in our data table, let me pull this up. Am I still sharing my screen? I think I am.
It's actually not up yet, Ren.
Thank you. Goodness. Further. Okay, and for example, we might want to pull out these pieces here. It looks like they're separated by underscores here. Okay, and that's a way in which this might be slightly messy. Let me do two things. One, we'll talk about how we can do that, but first let's go here. I posted this in the chat here, this website for tidyr, the tidyr package. And as you can see from this first line, the goal of tidyr is to help create tidy data. This is a very complex topic. Like I said, we could spend a whole workshop on this very specific topic, go into all kinds of details and so on. We're not going to do that there, but I'm pointing you to this particular website. And for example, there's this cool cheat sheet that you can take a look at that tries to summarize sort of problems with messy data and how the tools of tidyr can be used to help with those. This is extremely dense. I think it would be very difficult to go through this as a beginner, but it might, would be a place to start to look at some examples about using some of these functions that are provided by the tidyr package. Note that when we load the tidyverse, let me do that again here, actually here. Let me load the tidyverse package. It tells you what it's loading up. So you know what packages it's loading up. And you can see that tidyr is in fact one of the packages that it loads when you load up the tidyverse package. Okay, so we know that we have access to the functions in tidyr just by using this command here. Okay, let me show you how we might solve this particular problem. So let's read this annotation data file that we have. We noted that the run column here had multiple pieces of data here that we might want. We can use a separate function that exists in the tidyr package. In fact, let's take a look. Is it here in our, it should be here in the cheat sheet somewhere. Separate, so split cells here. Use functions to split or combine cells into individual isolated values. So the separate function in tidyr is the thing that we want. Let's zoom in a little bit here about the example. You can see this rate column had, looks like two numbers separated by a slash sign. We wanted, in this example, they wanted to separate these two numbers out into their own columns, okay? So that's what the separate command does. Let's see how that looks like on our particular data. So we're actually going to be talking about some of these things in the next session, but the separate command takes the input data table first. So that's this thing here. Then you have to say which column do we want to separate out. So that's the run column. We use this into, so this is saying separate the run column into, and we give it a vector. We know about this, the C operator. This just makes a vector, and we need to give new column names. We could call these things anything we want. We could, Joe and Sally and Susan if we wanted to, but that doesn't make any sense. Let's actually call them by useful names. So let's say this thing looks like a prefix of some sort, probably somebody's initials. This looks like a date, so we can call that a date, and we can call this last stuff out here maybe the sample. Okay, and then the last thing, you have to say, how do we want to separate the values in this particular column here, we can use the underscore to do that. So let's run this code and see what happens. Okay, so we actually got a warning message. I'll only talk about that in a second. But we can see what happened. It took this run column here and separated it out. So now we have the prefix in its own column, the date in its own column, and the sample in its own column here. Okay, so in one line of code, we were able to do kind of this relatively complex operation. It turns out if you look at this data table, there was actually some additional source of messiness here. If you look here for this first row, they used a dash here to separate sample from the letter here. But in the next rows, they actually used an underscore. Okay, so that was an inconsistency in the data. And actually that happened again on row 10 as well. Okay, so this was probably a typo, actually. Somebody probably inadvertently entered this a little bit differently than they expected. This happens all the time in real world data. It can be frustrating to work with, but it's the realities of that. And because of that, actually, we use this underscore to do the separation here, but that underscore doesn't exist in this case where it did in the other column. So it actually warned us that it wasn't able to get some pieces there. And as a result, you can see that on rows 1 and 10, it actually it retained this additional piece of information. Okay, so another piece of tidying this data might be to go and actually maybe update these things so that you can properly separate things out. Okay, so that's definitely more complex. We didn't cover that, but extremely useful. Again, go to the tidyr package, spend some time there, and I think you'll find lots of examples in there that would help you for working with some real world messy data. Okay. Great question. Thanks for the person who asked that. Okay, we're going to get into the meat of the day. This is our last topic we're going to cover. There's quite a bit here. We're going to try to take it step by step. I think the key thing here is to think about the high level concepts and look at some examples here, and hopefully that will give you a template that you can then use to work on some real world data when you get back to school or work. Okay, and it's the idea of using this dplyr package to do data manipulations. Okay, so the goal of the module here is we want to understand the set of fundamental operations that frankly underlie most of the common data manipulation challenges that people do. It turns out there's really a small sort of set of things that people actually need to actually do on data tables that encompass pretty much all the things that you may need to do. We're going to learn about this dplyr package and how it embodies or how it implements these fundamental operations. Then we're going to learn about this new pipe operator. This thing is really cool, but it looks weird. We already learned about the assignment operator that looks like an arrow. This pipe operator is supposed to kind of look like an arrow as well, kind of going in the opposite direction, going from left to right. We're going to understand what that is, and we're going to see why it's really cool for building data pipelines here. So dplyr is the package we talked about. The main assumption of the dplyr package is that when you use the functions, it assumes you already have a tidy data frame like we talked about. Okay, so that's the starting point. If your data frame is messy, then these dplyr tools will not work well for you at all. So make sure you have tidy data to start. And that's sort of main thing to note there. So what does dplyr do fundamentally? Its fundamental purpose and what it tries to do is formalize the fundamental operations that we use when we do data analysis. It does this by defining a list of functions that we can also refer to as verbs. And we use the term verbs because it represents actions that we're going to perform on data tables. Actions, manipulations. We're going to take data tables, we're going to manipulate them, we're going to summarize them, we're going to filter and subset them. These are all actions that we're going to do. And so we have this set of verbs or functions that we can use to get those things done. Fortunately, there aren't many of these verbs. Okay, there aren't many to work with. So, and they're named in such a way that hopefully you can recall them, understand what they are as you write your own code. And for me, I think really the key piece of what dplyr does is it allows you to focus on the question rather than the mechanics of having to answer the question. And the idea there is if you can somewhat precisely say the kind of analysis question you're trying to accomplish in words, that the code kind of flows naturally from that statement, the statement in words, which is really a cool thing to do. So it doesn't look like necessarily a bunch of gibberish code. It actually looks like something that kind of reads in a human readable format. And that's really cool. And put some more context here, I use dplyr, this R package, every day, all the time in my daily work. It's a really important piece of how I work with data all the time. And I think you talk to people that use this package, they probably agree that this is one of the sort of the key sort of game-changing aspects of the R language is this dplyr package for doing data analysis. Let's talk about these fundamental data manipulation operations. And this is the main set that the dplyr universe gives to us, and there aren't very many of them. So let's talk about these operations here. This first one is about adding a column here. So imagine you have a data table. One operation is you might want to tack on a new column to your data table. And why would you want to do that? Well, often that comes from you have existing data in your data table, and you want to do some computations on, say, multiple columns there. For example, you might want to add two columns together to get some new derived value. You might want to convert units of one column into something else. So the idea here is that you can add a new column onto your data. You may also want to add on external data to an existing data table that you have to add some new information. So that's this first operation here is adding the column. The second and third are about subsetting. Okay, we discussed this in some detail yesterday about subsetting vectors, about subsetting data tables, and we use the bracket operators to do that. We can also do those same kinds of subsetting operations using different syntax using the dplyr package. And there's two main cases. The first one is about picking specific columns. So this is really useful, for example, if you have like a data file with hundreds of columns in there and you only care about 2 or 3, you can subset to specific columns so you can focus in on the data that you're interested in. This next one is about filtering to specific rows. And remember, we use conditional expressions to do that. This is the idea that we want to get specific rows in our data table that correspond to some kind of condition we're interested in. For example, maybe proteins that we detected with a certain false discovery rate, or maybe a slice of our data from subjects that were older than 50 years of age. You know, these kinds of questions you would ask with this subsetting to specific rows. This next one is fairly straightforward. This is about just reordering the table. Sometimes you want to sort a table from high to low or low to high, and that's the reordering operation. These last two are a little more complex, but extremely powerful, and they're often used together in combination. The first one is about grouping subsets. Let's just motivate this with the idea that you have, you're measuring maybe data about a cohort of patients, and some of them are sick and some of them are healthy. You might want to ask, say, what's the average age of the sick population versus the healthy one? We could create a subset in our data frame by grouping. We can say group by their health status. Okay, we're just saying that in words. We'll talk about how to do this in code, but you could say, let's group by the health status. Then you can use this summarize operation to say, for each of those groups that we defined, what is their average age? Okay, and the idea of the summarize command is that it takes multiple rows for a given group. I've used red and blue here to note the two different subgroups in our table. And we're going to summarize those values in the blue square or the red square down to a single value, like an average age or a number of patients or an average p-value or something like that. That's what this group by and summarize does. So extremely powerful operations that I use all the time, and pretty much anybody that uses a dplyr package uses these operations all the time. I mentioned that dplyr represents all of these operations in functions, or these data manipulation verbs, and these are what they are. Hopefully the names reflect the operations that are occurring. So the mutate, think of like you're mutating your data frame. You're like sticking a new arm or something on your data table. That's like adding a new column. The select and filter are hopefully straightforward. We're selecting specific columns or filtering specific rows based upon a conditional expression. The ordering is probably straightforward. We're just arranging the data table on some criteria. And then these last two are really, straightforward as well, sort of grouping by a certain values in our data and then summarizing values within their group using the summarize command. Okay, so these are the main verbs that you'll need to know and learn and memorize when working with dplyr pipelines. Do you have any questions on this sort of intro material that we should bring up? Of course, we haven't gotten into any code yet. We're going to get there in just a bit. Let me talk about just the fundamental operations of how these dplyr functions, these dplyr verbs work. They're functions, so again, they have a name and you need to wrap them in these parentheses. The first input to these functions is always a tidy data frame, okay? For all of these functions, the first thing you provide always has to be a tidy data frame, no exception. These commands often have additional pieces of information that we have to provide to it. I just put ... here, but there would be other code that would come into here. And we'll see examples of some other things. For example, sometimes we have to enter a conditional expression, and so we would provide that conditional expression after we provide the input tidy data frame. It's also important to know that what these functions give back to you, what they return to you, is also a tidy data frame. So you give these functions a tidy data frame, it gives you back a tidy data frame. It's probably been manipulated in some way because that's what these functions are doing. They're manipulating the data table, but it's important to note that you give it a data frame, it gives you a tidy data frame back. Okay. Oftentimes you might want to assign that to a new variable. And so you usually do the assignment operator back to a variable name. And so for this case, what we call the mutate command on this mydf data table, what comes back is a new data frame that has a new column, okay, that we defined. And we stored that in the mydf2 variable. It's also actually quite common to reassign your data table. You'll start with the data table and then you'll sort of reassign it back to itself. That's essentially just overwriting the data table with its updated manipulated form. That's common to do as well, but you can save it to a new variable or back to the same variable as you choose. Okay, let's look at some specific examples here of using these verbs with explicit code. We're going to look at this data table again. Let me bring it up here just to recall what this thing looks like. It's this annotation data table with these three columns, run, condition, and bioreplicate. So this is the thing that we're going to be looking at in these examples. Okay. Okay, so let's talk about the mutate command. Why do you want to use mutate? You use mutate whenever you want to add a new column to your data frame, and oftentimes this is based upon data in existing columns here. Okay, so that's sort of the use case for it. If we want to use these dplyr verbs, we have to load the tidyverse package like we're doing, and we need to load up a data frame here. So that's what this code is. We've been doing this over and over again. So hopefully you're familiar with that. Let's look at this. Admittedly, this is very contrived and not too useful, but just think about the spirit of what this is. So what we're asking here is we want to add a new column to the data frame that is 10 times the value of the bioreplicate column. And remember the bioreplicate column, sorry, I'm jumping back and forth. The bioreplicate was just integer 1, 2, 3, and 4. So let's say we wanted to add a new column onto this that had 10 times this value for some reason. Let's show the code that does that. We're going to use the mutate command because we're adding a new column. Remember, the first argument is always the input tidy data frame. So we start with that, and then we have to define the new column that we want to make. The first thing we do is we need to give the name of that column. Okay, so I just decided to call this rep times 10 to make it descriptive. We put an equal sign here, and then we give a mathematical expression that does that piece of math. So it takes the bioreplicate values and multiplies them by 10. Okay. In fact, let's just show you what that looks like. We won't, in some of the exercises, I'm going to go and ask you to go and do this yourself, but let's just take an example here of what that looks like. So let's actually not assign it to the variable. Let's just see what that looks like. So we're going to mutate on this data frame and make this new column called rep times 10, and it's going to be equal to this bioreplicate value times 10. Let's execute that. Okay, got the same, remember these functions always give you back a data table. So that's really important. So we got a data table back out. It's the same thing as before, but now we've mutated on a new column here called rep times 10. And you can see, in fact, it's 10 times the value here. So just as we expected. Okay, so, and if we wanted to, we could have assigned that to a new value if we wanted to store that manipulated version. One of the syntax things with, and this is a little bit with quirks with R in general, is we didn't put quotes around these names here. Okay, these were column names. You wouldn't put quotes around them. It's a way in which R works and way in which the tidyverse works. So just note that we didn't put quotes around these. We just listed the names as is without quotes. Let's talk about these next two examples. These are about the filtering operations. You can actually answer these filtering operations right now using the information we learned yesterday about subsetting vectors and data frames. This is another way to accomplish those same tasks. So we use the select verb when we want to get specific columns in our table. So pretty straightforward. We can load up our data like before. We use the select verb with our input data frame. Next, we give a vector of the column names that you want. We know the C function, that's the combine function. We've been using that over and over to make vectors. So you just provide a vector of column names here. And this will give back a data table where it just has these two columns there. Okay, so that's a fairly simple, straightforward thing to do. The filter command is perhaps often one of the more powerful features. This allows us to get specific rows. This is when you want to, again, sort of hone in on specific subsets of your data for some reason. Let's load up our data table. We're going to use our filter, our filter function. We're going to provide our data frame. Now we have to provide a conditional expression, exactly like the expressions that we learned about and used yesterday. So that's a key piece, a tool that you're going to be using over and over again, these conditional expressions. And in this case, we want to get the condition, the rows of the data frame where the condition is equal to condition 4. Let's actually do that here in R as well. So here's our data table. Let's write our conditional expression by itself. We do it a little bit differently, but condition expression double equals condition 4. Remember, that gives us back this list of true and false values where that condition is equal to condition 4. Let's write this in terms of the tidyverse way sorry, let me do this, the full example. Let's actually subset to that using the bracket subset operators. So we write the data table, we use our square brackets, we give the condition of the rows we want to filter to. We have to put a comma and then the closing bracket. So we've done this a couple times. This will give us back the data table where we only have the conditions, our condition 4. Let's rewrite that in terms of this new syntax that we just learned with the filter command. So we can use the filter with that data frame. Now we need to give a conditional expression. Let me write it out and then I'll describe it. So condition equals condition 4. Let me execute this. And you can see we got exactly the same result in two different ways. Here we got that result using the information that we learned yesterday. Now we're using this filter command to get the same thing. One important note is that we didn't have to use this $, syntax inside of the filter command. Okay, and the reason, that's just the way in which this dplyr package works. Essentially what's going on is as soon as you specify this data table here on the front, it assumes that you are referring to columns inside of that data frame. So there's no reason that you need to type that $, referencing condition again. It assumes that you are working in that data table, cuts down on the code, and you don't need to refer to it that way. Okay. Any questions about that filter command? just combining two concepts, the idea of calling this filter function and then providing a conditional expression. Okay. The arrange command, this is almost more for sort of visual representations a lot of times, but this is just sorting the table. And this is pretty easy to use. You use the arrange, the input data frame, and then you provide a column in your data table that you want to sort by. So you can sort, in this case, the condition is a alphanumeric kind of data. So it will do alphabetical sorting of that data. So it's going to rearrange the data table, sorted in alphabetical order using the condition column. You might want to sort in reverse order. In order to do that, we have to use another function. This is DESC, standing for descending. So it says, sort this on descending condition order. This is just some syntax. We have to just use this new function. Nothing special about it, just that you have to remember that this function exists, and you need to use it if you want to do sorting in descending order. If you were to provide a number here, it would do numerical sorting on the data. This last set here is definitely a little more complex, but is really useful and really powerful. It's this group by and summarize sort of recipe for writing code here. And let's say the question you're trying to address is count the number of runs per condition. I have some notes here, but let me actually just do this live, and I'll ask you to retype this in the exercises here. But let's look at our data table. We want to count the number of runs associated with each condition here. Okay, so the first thing we want to do is we're going to use this group by command. We want to group our data frame by a certain column here. In that case, it's the condition column. So let's group by the condition. Okay, this isn't going, if we look at the output here and compare it to what we had before, this didn't actually manipulate the data itself. We still have the same data table, but note that it has this additional little information line that says now we have groups in our data. It's grouped by condition, and there's 4 of them. So what this grouping command has done is essentially made 4 little data tables internally. Okay, it's 1 for each condition set here. And sort of those little mini data tables are available now for us to do something with. Let me show you an example. Let's say this to a variable. Let's call this grouped data, something like that. So now we have this grouped form of the data. Now we can call this summarize command that says, given those groups, let's compute some summaries on each one of those groups. So we can call summarize on this grouped data. And what do we want to do? We want to count the number of essentially experiments that are associated with that. There's a variety of ways to do that. Let me see, what did I say in here? So we could say, how long are the runs here? What's the length of this run vector here? So we can say length run with a capital run. And let's take a look. Okay, this is a cool thing. Now we've got a new data table that's popped out, except now we have 1 row for each of our conditions, the grouping variable. That's what we wanted. We wanted to count up the number of runs per group. So now the output is 1 row per group, and then the summary value. When you run the summarize command, you're almost always going to want to name this column something. So let's call this n runs. So we'll put that in front and put the equal sign there. And now it will name this new column that we created, the summary column, as n runs. And so we know that we have 3 runs for each condition. Okay, imagine you ran a big experiment with hundreds and hundreds of runs or something. This would be a nice way to QC it to make sure, hey, I expected to get 10 runs per condition. You could run this quick group by summarize command to confirm that that's the case. And maybe you'll find, oops, we only ran 9 experiments for this particular condition. What happened? Well, whoops, we forgot to upload the data file to our server. It never got processed. And so, that's a nice way to QC data. Okay. We're going to see more examples of this group by and summarize in some of the examples here coming up. Okay, let me come back here. So again, just the note here is that we group by, we make this group data frame first, and then we summarized on that group data frame. If you were to provide the data, the ungrouped data frame here, you would get a different result. In fact, let's do that just to see what that looks like. Let's say we forgot in our summarize command, we forgot to give it the group data. We just gave it the original data frame. It actually just does a very high level summary here where it just computed the number of runs here. There are 12 runs here in this data table. So that's probably not quite what we wanted. So that's why you need to group first to get the output that we actually wanted. Okay, let's go back to PowerPoint. Okay. Okay, so we talked about use cases for each one of these verbs and some cases where we might want to use them. We're going to go into some exercises here. I want you to try running, go back to the select and filter examples here. Just run these, just get used to typing the code a little bit and looking at the output. This is the same thing, same kind of stuff we did yesterday. So maybe if you can recall from yesterday, can you retype that same kind of code using the subsetting operations that we did yesterday? Don't worry if you can't do it. That's not the key thing, but just noting that there are multiple ways to do this. And then also I want you to run that group by and summarize example that I just ran. I want you to actually go and do that yourself and sort of pay attention to the code and what's there and get comfortable with that. All right, so let's take 5 minutes or so to do this. Actually, it's 37. So let's come back at 45. So 9:45 or 12:45. Let's come back then, and we will reconvene to talk about the last little piece of the puzzle here, talking about how we can use these verbs in pipelines. So come back at 45 on the hour. Please try these examples out. And go ahead and ask any questions here if you have them about these verbs, working with these dplyr verbs. Devin or TAs, any other questions come up that we might want to cover?
I don't think so. I'd just say if anyone has like a lot of questions on this kind of content, we can do a breakout TA room as well. And just let us know in the questions.
Thank you. There was a good comment about typing commands in the editor instead of the console. Yes, I definitely will do that. Apologies there. That does make sense to do that. And also, obviously, the code is also in the slides, but also I've been typing some code that's not in the slides, so I'll leave it in the editor there, so it will be easier to see and keep track of. Thanks for that. There was one question about the difference between select and filter. They're similar in terms of providing subsets, but associate select with columns. So select is what you use when you want to get specific columns of your data. Filter is used when you want to filter rows. And I realize that those could probably be used oppositely. It just is how the package designer decided to name those functions. So select is columns, filter is rows. There's a question about rerunning the library tidyverse command. So think of your R has a session associated with it, sort of like the session in which it's doing work. And if you start up a new R from scratch, it has a brand new session. And so when you do that, when you execute the library tidyverse command, you only need to do that once per session. Essentially, it will load those packages up for you, and then you can refer to them. You don't need to keep rerunning the library tidyverse command over and over again. Now, I have to say in my slides, I did include that. Let me bring that up. In my slides, I did, in these examples, I did call this over and over again. I did that to make all of these sort of pieces of code sort of standalone if you were just to do one example by itself. But for example, you don't need to load the data over and over again as well. As long as you're in the same session, these variables and the loaded packages will persist. So you don't need to rerun these things over and over again as long as they're in the environment. Okay, we'll come back in about 1 minute here. And one thing I'd like to note that I really like about coding in general, and that's the idea that your laboratory is your coding environment here. Like as a laboratory scientist, you might have a question: what happens if I were to change the concentration of a particular reagent? How would that affect my experiment? And a lot of times to answer that question, you'd actually have to go into the lab and prepare your experiment and mix your reagents and all those kinds of things and perform your experiment. That can be very time consuming to do. The cool thing about code is you might have questions about things. What if I did this thing instead of that thing? The cool thing about coding is you can just go and try it. And that's how you can learn a lot of things. But trying to break things, trying to do slight variations or modifications on things. The nice thing is you can just type that code and hit return and see what happens. There's a very, 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 very low probability that you would actually like mess something up. Like you're probably not going to delete all the files on your computer, for example, by just, you know, typing out some R code that's incorrect. So feel free to experiment. I think that's really important. So if you have a, you know, after this course, if you have questions about R, what if we did this instead of that? I'd say one thing you can do is just go and try it, type the code out and see what happens. Now, you may not understand what actually happens when you execute the code. That's probably more than likely going to happen, particularly as a beginner. But at least it gives you some experience about what can happen and maybe provide some things that you could Google search for to try to understand in more detail. All right, so let's come back here. I hope you executed some of those expressions. Hopefully you're able to get some of the same results that we were seeing when we looked in the data. Let me, there was a nice question I think that popped up, and the idea was that can I do summarizations on multiple columns here? So as somebody recommended, I'm going to type the code up here in the editor so you can see it more persistently. So that was a good suggestion. So remember we had our grouped data, and what did we do? We group by our data. It was a condition, I think. So we grouped the data by the condition here. Let's do that. And when we looked at it, we could see that it was the same data table, grouped data table, except now it has some grouping by condition. Somebody asked, what if we wanted multiple summaries? We didn't just want to do one. We just didn't want to count the number of runs. We wanted to do something else. We can definitely do that. So let's try this. Let's summarize the data. And we can just keep providing ways to summarize the data. So let's say n runs equals length of the run column. Let's say we want to get the max bioreplicate. This data is, it's a simple data table for us to work with. It doesn't it doesn't do too much here. The bioreplicate is the same for every condition here. So in fact, the max doesn't really matter whether it's max or min or whatever, but just bear with me as imagine we wanted to do that. So max biorep equals max of the bioreplicate column. Let's look at the output of what this is. Sorry. Okay, I just made a mistake here. Notice that I did not provide the grouped data to the summarize function. And in fact, we got this unexpected result. So always look at your results here. It's important to do. Let's actually provide the group data. That's actually what we meant. And let's run that. So now, and let's compare that to the first example where we only provided one summarization here. Okay, so let's take a look at that output. This gave us two columns back, the condition and this new summarization based on the number of runs. But there was no reason we can't just put another comma here and do another summarization, which is the max of the bioreplicate. Let's run that. And we get a new column here. So in fact, you can put all kinds of stuff there. And in fact, a lot of times I have these summarization commands, and sometimes I even put a new line where I just like keep going and doing all kinds of summaries, calculating the mean of the intensity values, calculating the standard deviation, and then I'll calculate the CV from those mean and standard deviation values, and then I'll convert that to a %. And I just keep running down these different summarization commands, and all of a sudden you've done like a ton of math in a relatively short amount of code. You can imagine trying to do that in Excel where you're sort of clicking the cells and dragging things down and all that kind of stuff. This is an actual case where you can sort of type it out in code and do all these complex operations really quite quickly. So it's pretty cool there. There is one concept remaining that we're going to cover that will hopefully bring all these things together into something really quite useful for your data analysis work. That is the idea of the pipe operator. Okay, just like that arrow symbol that we use for assignment, it's actually multiple characters. It looks kind of weird and kind of cumbersome to type. There's also the pipe operator here. It looks like the % symbol greater than %. These all have to come together, no spaces between them. This is known as the pipe operator. And think of this as I mean, the name, the pipe, imagine you have like a physical pipe that something goes in one end and comes out the other. That's what this is supposed to represent. And this greater than sign is supposed to sort of note this left to right flow of information. So this pipe operator takes an input on the left side and feeds it into a function on the right side. Okay, that's all it's doing. It's kind of simple in concept and actually simple in action here. So let's think of an example how this relates to all these tidy data frames and these dplyr functions that we've been talking about. So you can take a tidy data frame and feed it into a dplyr verb. We pipe it into it. We say we pipe the data frame into this verb, and this produces a modified data frame. Okay, so we're just looking sort of abstractly here at sort of these templates about how we can think about these pipelines. So here's the template. Again, tidy data frame, we pipe it into a verb, and that produces some kind of modified data frame. So let's translate this for the different verbs we already learned about. Let's take a tidy data frame and pipe it into the mutate function. What do we expect to get out? We expect to get out a modified data frame that has a new column, because that's what the mutate command does. We take the tidy data frame, we pipe it into the select command. We expect to get out a new modified data frame with only the columns that we selected. The filter command, we take the tidy data frame, pipe it into the filter, and we get back a new modified data frame with only specific filtered rows. Okay, so you can see it like we're just doing the same thing over and over again, taking an input, getting a modified output using this pipe operator and these dplyr verbs. Okay, so that's one idea here. We need one little other piece before we talk about pipelines in particular. I am going to tell you that these two lines of code do exactly the same thing. Okay, exactly the same thing. This is code that we've been writing without pipes. This is code that we're writing with pipes. Okay, these things again do exactly the same thing. Can you see the similarities and the differences between these two lines of code? So let's take a look at that. Essentially, this pipe syntax does something really simple. It takes the first input, it moves it out in front of the expression. You add this pipe operator, and then you provide the rest of the function information, excluding that first argument, that first input. Okay, so we essentially are just taking this input, moving it to the front, and adding the pipe operator, and makes this. All the rest of the stuff has to just follow as going. So actually, let's take a look at this here. Let's run this code so you can see it. Here, I'll run it up here. Okay, so this is something we just did in the examples. We filtered the data frame for the condition 4 rows. We got this out. I'm going to rewrite this using pipe syntax, pull the data frame out. We're going to use the filter command, and we do everything else except that first little piece of the puzzle. And we put the condition in there. And if we run this, we get exactly the same output. Okay, so this is just two ways of writing exactly the same thing. Okay, you think, oh, okay, why do we care about that? Why is that important? Well, I'll show you, because it's really pretty cool. Okay, so let's build. Let's not worry about the practice time, because I just showed you. The idea was I just wanted you to practice writing one of these pipes, but I just showed you in real time. Let's get to the meat of the things here. So here's the idea. We take a tidy data frame, we pipe it into a dplyr verb, we get out another data frame. It's been modified, but it's a data frame. So there's no reason we couldn't take that modified data frame, pipe it into another verb to produce another modified data frame. Essentially, that allows us to take an input and pipe it into a bunch of different verbs to do some kind of interesting computations, answer some kind of interesting question about our data. And we can do that using this pipeline syntax. This is what I mean by a dplyr pipeline. And it's a really powerful way to think about and work with data. Let me give you an example here. We're going to have another example with that bigger data table that we looked at the very beginning, perhaps maybe a little more interesting questions that we'll answer, but the same concepts apply here. So again, with this data table we've been working with, let's do the following. I want you to give me the output where we only have the bioreplicates values of 2 or higher. And then I want you to count up the number of runs per condition. Then I want you to order the results based upon the value of the condition here. Okay, so again, a little bit of a contrived example, but we're doing multiple things here to arrive at the answer. Again, if you've already loaded your library and the data, you don't need to do this again. This is what that dplyr pipeline would look like to accomplish this task. We take our input data frame and we pipe that into the filter command. We want to get bioreplicate values that are 2 or higher. So we just provide this conditional expression that does the filtering there. Then we don't need to save a variable. Don't need to save a variable or anything. We can just pipe the output of this. If we were to run this command here to here, we would get a modified data table. So just imagine that modified data table exists here. We can now pipe that modified table into a group by the conditions that count up the number of runs per condition. Okay, we did this in another example, but now we're combining that idea here. This is now again another modified data table that has the conditions and the number of runs. Then we can sort that output table using the arrange command in descending condition order. Okay, so the cool thing about this is it kind of reads in English how these steps are here. So it says first, only get the bioreplicates values higher than 2. So filter to the bioreplicates greater than 2, greater than or equal to 2. Then I want you to group by the condition and count up the number of runs. Then I want you to sort that table based upon the condition. Okay, so kind of how you say that in English kind of maps back to the code that you actually wrote, which is really pretty cool. So let me take this example and run it through a little bit by bit so you can see what's going on here. Let me do this up here in the editor, and we're going to do it piece by piece so you can see what's going on. Sorry, let me also note it's very common with these dplyr pipelines to write them on multiple lines. And why is that the case? Well, I'll show you. If these are not on multiple lines, you can see that these pipelines become very, very long lines of code. Okay, and these pipelines can actually get even longer, and they're hard to read. So it's very common to put them on multiple lines of code for each little step that you're doing. It's just important to note that the pipe operator always has to come at the end of the line. Okay, so don't put the pipe operator at the beginning of the line. Make sure the pipe operator is at the end of the line. Okay, that's the key thing. Let's take a look at this first little piece of the pipeline here. And actually in RStudio, you can use your mouse, highlight it, the piece of the code that you want, and then you can just click the run button or command or control return, and it will just run the code that you've highlighted. So let's run this. So this first step filtered to the bioreplicate values that were greater than or equal to 2. Okay, so we can see what this table is. Now imagine in your mind that this table exists in R's memory, and it's going to feed this table now into this next step. We're going to group by the condition. Let's run the pipeline up to there and execute this code. Again, the group by just essentially just puts a note that it's now grouped by things, and it's grouped by the condition here. And actually now we only have 3 groups here because we did this filtering command. We took out the bioreplicate of equal to 1. We can use the summarize command to count up the number of runs per the condition. That gives us this data table now. This looks quite different. We've done a summary now. Now we only have 1 row for each condition and the number of runs associated with it. Then we want to, for some reason, sort this thing in descending condition order. So reorient this so condition 4 comes first. And that's what the arrange command does. So now we have the condition from high to low in terms of alphabetical sorting. Okay, so this is an example of the dplyr pipeline where we did lots of computations here in just a few lines of code. Imagine trying to do this in Excel, for example. I think you would find that it would be actually quite a bit of work to accomplish the same kind of task, where we can just write this in a few lines of code. All right, so that was a pretty heavy section, I would say, but hopefully the main concepts made sense and maybe some motivations about why you'd want to do these kinds of things. Next, we're going to do some exercises in an exercise sheet, and we can take a little break as well. Just wanted to check, are there any specific questions about this dplyr pipeline? Anything that didn't make sense about what we did here? Of course, you can continue to ask questions in the chat. What I'm going to recommend here is let's take 15 minutes now. You can combine that, with a break. We'll come back at 10:15, but let me show you where I'd like you to go. If you're in RStudio Cloud, or if you're on the GitHub site, let me go to the GitHub site here. I want you to take a look at, in the exercises folder here, the day 2 exercises with dplyr. Okay, the solutions are there. The solutions are on GitHub. I would like to recommend that you don't look at the solutions right now. So take a look at the exercises. In RStudio Cloud, the files are already there. You can bring up day 2 exercises. And what we're going to do, this is maybe a little small here, perhaps. Let me bring them up in my editor over here. Day 2 exercises. Let me make this a little bigger. We're going to load up this big input file with 1.2 million rows of mass spec data, and going to ask you to go through some of these exercises here. We're going to do some filtering with the subset commands. We're going to do some group by and summarize it. And then, for example, we're going to try to count up the number of unique peptides per protein. We did that very specifically for one individual protein in the previous example. Using dplyr, you can actually ask this question for all of the proteins in your data and get it in a nice output using relatively little lines of code. So anyways, work through that. There's some more challenging exercises here at the end that you can go through. You may not get to these immediately, but you can certainly work on these after the course, and the solutions are going to be posted online. All right, so let's come back at 10:15 and we'll take a look at these answers. Go ahead and ask any questions you have too in the chat if you need to. And TAs, if any questions come up to answer live, we can do that as well too. Okay, one question came up. How do you generate a new table with the pipe operator? Let's see. Usually you have a data table to start with, like you get one from a read CSV command or something. So usually you start with a data table. You don't really use the pipe operators to generate a new table from scratch, for example, if that's what you're asking. There is a package called the Tibble package if you want to make a data frame by hand. I'll post a link to that in the chat to give you some information about that. But typically, you usually have your data table to start with before you start using the pipe operators. Oh, okay. Yes, I will keep sharing my screen. Let's see, I don't know if you want to see something in particular, but here we go. If there's some piece of information somebody wanted to see, I can bring that up. Let me go to the chat. So about making data frames also. So if you want to make a data frame or tibbles as they're called in the tidyverse language, you can take a look at this link about the tibble package. Great question, Susanna, about exporting your table after you work with it in R. Great question. So a variety of ways to do it, but we did not cover this, but there is a, so if you look in the readr packages, there are read CSV functions. There are also write CSV functions. Okay, so and it works kind of the same as the read CSV, but let me get a data table here. Let's call this output data table. So this is the result of our that dpyr pipeline that we ran. Let's take a look at that. So output df looks like this thing. Let's say we wanted to save that for some reason. So we can use the write underscore CSV function. The first argument, the first input has to be the thing you want to write out. So that variable name, then you give it a name, my output.csv. Okay, so I'm going to run this command and it's going to write a file out. If you look over in your file browser over here, you'll see we'll have a new table, a new CSV file here. And if we view that file, we can see we have a CSV representation of that output data table that we just made. Okay, that's a great question. Okay, so just like the read functions, we have write functions as well. Do you have to include the file extension for output? That is a great question. And what I would recommend is let's give it a shot. Let's see what happens. Okay, let's just do it. Nice thing about coding. Let's call this my output 2. Let's not add the extension. Let's see what happens. In this case, it did not add the extension. Actually, to tell you the truth, I would have hoped that the write CSV function would have done that for us if it didn't provide the extension. But in fact, it's doing exactly what you tell it to do. So this is actually still a CSV file in its contents, but it did not append the extension. So let's do that, add the extension, and then we can see that it showed up here. See, I think I saw another question. Sorry, I'll just talk in the background as people are working. Hopefully it's not too distracting, but somebody had asked a question about if we wanted to add the number of runs to the original data frame, and we can definitely do that without the summarization. So we have our group data here where we grouped on condition. What grouped that? You'd have to think about what kind of verb do we're going to add a new column. What verb do we want to add on for the new column? That's the mutate command. So we'd use the mutate command instead of the summarize command that would add a new column. It would still compute on the individual internal groups, but it would still retain the original data frame. So let's take a look at that. So mutate on the grouped data and runs. It's the same kind of syntax, equals length of run. Let's run that code. I'll put that up here. Okay, so we have our original data here. We still have the same outputs, but now it's in the original data frame. Okay, so now in the previous one where we used summarize, we took those multiple rows and summarized them down to a single row. If we just use the mutate command, we're going to take that group data, still calculate the summaries on each group data, but then keep that original column here so that those persist. One important little piece is that when you're done with group data, you need to call this ungroup function. Okay, because if we look at the output, our output is still grouped. And typically we don't want that. That could cause some problems down the line. So if we don't ungroup it, then we need to call the ungroup function. Interestingly, the summarize function after you call the summarize will do the ungrouping for you automatically. So that's a little complex of a topic, but just something to note. If you use a mutate after a group by, that you want to use the ungroup function, and you can pipe that into the ungroup function just like this to ungroup the output. So you no longer have a grouped data frame. Okay, we're going to take about 4 more minutes here. Yeah, so a question, is summarize different from aggregate? So I talked about yesterday the idea of looking up documentation for different functions. And I just want to review that. You type the question mark, like I'm asking a question, and then you provide the name of the function. So let's look at summarize, like that. We can get information about the summarize command here. We can also do that with aggregate. So a couple things here. Let's look at the summarize documentation first. This summarize, at the very first line, it tells you which package this comes from. Okay, so this summarize function comes from the dplyr package that we just talked about and gives you just information about it. Let's look at the aggregate command here. The aggregate comes from the a fundamental core package of R, the stats package, aggregate. And this splits the data into subsets and computes summary statistics for each group of your subsets. Okay, so this sounds a lot like the group by and summarize ideas that we talked about here. In fact, there are ways to in all programming languages, there are often multiple ways to do the same thing. And so you could use aggregate to answer some of these same questions that we already talked about with the tidyverse. However, and this is by no means, I'm not trying to speak down on sort of this is known as base R, the base R way of working with things, not trying to say anything bad about the base R, but some of these functions are older in style and how they work and operate. The tidyverse versions of these things are considered the modern way of doing data analysis in R. And it's down to a matter of preference, but I prefer working in the tidyverse. I think it's an easier way to write code and operate on code and work with data, as opposed to some of these really powerful functions, useful functions in the base R installation. And aggregate is one of those base R functions. So you could, by all means, use aggregate to do these split subsets and compute summaries. I prefer to use the tidyverse. It's a more modern way to go. And to be honest, I think the community is kind of moving that way as well. I think people really see the power of the tidyverse and tend to use that over maybe some of these older ways of working with data. Okay, let's give it 1 more minute here. Again, let me just reiterate that the solutions to these exercises are on the GitHub repository. Where, if you don't know where the GitHub repository, go to the May Institute website, scroll all the way to the bottom, and you have key links in here, including the GitHub repository. The exercises and solutions are already uploaded, so you can take a look at those on your own time as well after the course. Another tip, if you haven't worked with GitHub too much, if you come to this green button that says code, click on the button and you can download the entire repository as a zip file. You'll get everything here, including the lecture sizes, the lecture slides, the exercises, and the data, as well as some additional information and links here. Okay, so if you want all the information we've been talking about, just come to the GitHub repository, click code, and click download zip, and you'll get everything. Okay, we're wrapping up here. I don't think we're going to take all 3 hours necessarily today, but let's go over some of the solutions here to some of these pipeline examples. And I want to in particular, I want to walk through the example where we calculate the number of peptides we detected per protein. So first, we need to load our tidyverse package and read in the data. Again, this is a big data file, 1.2 million rows. So this is, a real world data set in terms of its size. Okay, so won't go through, I won't execute these examples here, but this is about subsetting to rows using filter command. I also provided here the syntax we learned yesterday using the bracket operators to do the subsetting. So you can actually do the same thing in 2 different ways here. Talked about filtering data here. What was interesting, I think, here is that you can filter multiple steps. Let's say you want to filter on one condition and then filter on another condition. So in this particular example, I asked you to filter down to a specific protein and then to a specific mass spec experiment, some raw file. So we used a pipeline here. We took the input data, we did a filter command for the protein name, then we piped that into another filter command for the file name. Okay, so we did 2 filters. You're free to use these commands in whatever order the order needs to make sense for the analysis you want to do, but you can put them in any order that you need to and do them as many times as you need to get the work done. Okay. Let's look at this idea of, let me quickly go back just to motivate this. Let's go back to, I think day 1, working with data frames exercises. Do I have that up here? I think we covered this. Actually, I want to go to the solutions. Solutions. We covered this morning where we calculated the number of unique peptides for a very particular protein here. Right? We went through this and there was lots of lines of code here. We first subsetted to that protein. Then we got the peptide sequences. Then we got the unique peptides, and then we counted those up. Okay. So there was quite a bit of code here to answer this question. That was just for one protein. Okay. Let's look at what a dplyr pipeline looks like to answer this question for all proteins in our data set. Let's take a look at this again. Again, we have a bunch of proteins here, a bunch of peptide sequences, and we want to count up the number of unique peptide sequences per protein. That's really simple to do with dplyr. We take our data frame. We want to group by the protein name. Then we use the summarize command to make a new column called mpeptides, and that's just the length of the unique peptide sequences. Okay, so we use 2 functions here. First, we got the unique sequences, then we got the length of those. Let's run this pipeline here. And now we got 3,000 rows here for each protein here. We got the number of unique peptides that are present. And that, actually, let's view that. We can use this, remember this view command. Oh, sorry, let me save this as a peps per prot. Save the output of this pipeline here. And let's view peps per prot. I gotta spell it right, that's really important. Okay, so now we have this data table that we can now look at, and now for each protein, now we have the number of peptides here, right? So that's pretty cool. So in 3 lines of code that's actually pretty human readable here. We did actually a ton of computations here. And you can imagine now we want to take this data and we can pipe this maybe into ggplot2 and make a histogram of the number of peptides that we detect per protein. Okay, that might be a common thing you might want to do. We did that really advanced computation here, just using a couple lines of code. And hopefully it makes sense. Take the data frame, group it by the proteins, and count up the number of unique peptides. Okay, so how you say it in English kind of maps almost directly to how you write the code in practice. I give you another example here of another pipeline you can go through and work through those. Again, these are in the solutions, so you can work through those as well. Okay, great. So any questions from the audience on that? Some fairly complex topics there, but hopefully you can start to see the power of the dplyr framework, the power of these data manipulation verbs, and how you might actually use these in practice. Any questions particular to bring up? And also we can stick around at the end if you have specific questions, and we can share screens as needed as well. Okay. Well, actually, let me just take a look here. Okay, sorry, this is a great question. Should we add library dplyr? So let me, the answer to that is no if you do library tidyverse. Well, sorry, the answer is yes, you can do library dplyr and get all of those functions. The tidyverse package is a convenience package that loads lots of these libraries that you typically use in typical data analysis. So let me execute this again and look at the output here. This will only occur on the first time you use this library command. It tells us what packages it's actually loading. And in fact, tidyverse, or dplyr is actually one of those packages. So you don't need to explicitly load the dplyr package because it's being loaded when you use this library tidyverse command. Okay, and that's just a convenience function because you often want the data reading functions. You often want dplyr. You often want ggplot2 available so you can make plots. Okay, let me, we're getting to the end now. So we covered the main material here. I have one homework assignment for everybody. I would like you after this course to, sorry, let me get into that. This is another great question. What do the conflicts mean? So I'm telling you that it's usually very safe just to ignore these conflicts. But what this is noting is that the dplyr package has a function called filter. But in one of these base packages that comes with R, like when you start R up, there are some of these base packages that are made available. One of those is stats. The stats command also has a function called filter. So these have the same name. Okay, so if you type filter, which one is it going to use? Is it going to use the dplyr one, or is it going to use the stats one? This conflict says that the filter command is going to use the dplyr version of that, not the stats version of it. Okay, and same with this lag function. And for all intents and purposes, when you're working in the tidyverse, that's what you want. So it's mostly safe to just ignore those conflicts. All right, good question though. It does look a little intimidating, right? When you load this, you see these red squares and conflicts. It seems like it's bad. Just when you're working in the tidyverse, it's most of the time safe to just let those be. Okay, so the homework assignment I want everybody to do. You're probably doing some data analysis somewhere, maybe in an Excel spreadsheet, for example. Maybe you have some other piece of software, Jump or something, that you're doing some data analysis. I'd like you to take some simple data analysis that you're doing right now, and I want you to try to put that in the framework of a dplyr pipeline, like we've done here. Okay, it starts with something simple. It doesn't have to be fancy or complex, but I want to see if you can translate some existing analysis problem that you're doing into the language of R and into the language of dplyr. And in fact, you can compare your results to see if you're getting the same results from the two approaches. Okay, so that's a homework assignment for you to go and try out after the course is over. Let me now just bring up some wrap-up slides here. I want to provide some context and summary for what we went over, as well as some additional resources that you can continue to use and work with. as you continue your R educational journey. So what did we learn? We covered some key topics here. We learned about working with R in RStudio. We learned some basic R syntax and covered these 4 kind of main topics here. That was in day 1. We learned how to work with vectors and data frames. We learned how to read data into R. And then today we talked about tidy data and then using dplyr to do these data pipelines that can actually be very powerful in data analysis. Yesterday, I had listed a list of things that we were going to cover. And so I hope you may not be an expert at all of these topics here, but I hope that at least you have a basis for being able to do these kinds of things. So hopefully you can start up RStudio and use it to write code. Hopefully you understand the ideas of variables, how to create them, how to assign them, and how to work with vectors and data frames and do operations on them. We learned about those read CSV functions to read CSV files into R. Hopefully you have some idea about what tidy data is and why it's important. And then, like I said, with that little homework assignment I'd like you to do, hopefully I'd like you to go back and take some real world problem that you've solved using Excel or some other program and see if you can translate that into the language of the tidyverse in these dplyr pipelines. There are all kinds of resources available there. I haven't listed a ton here. I didn't want to overwhelm you, but I wanted to focus in on some key ones. So let's take a look at RStudio's learning references here. There's a great set of materials here, including sort of courses, online courses, books, all kinds of things here, great learning resources here. And in fact, also they're linked here. There are some of those cheat sheets. We looked at one of those for the tidyr package, but there's also lots of great books and tutorials that you can use. So this is a great resource to start for beginners, and they have other resources for intermediates and advanced as well. So this is a great landing page you can go to learn more about lots of the topics that we covered in the course. There's a tidyverse website. You can go there to learn a little bit more about the packages that are there and the kinds of things that you can do. There are 2 particular books I'd like to recommend. This first one is Hands-on Programming with R. It's completely free. It's written by Garrett Grolemund. He's a great trainer and educator. He works at RStudio. He's just a really good teacher. He's written this book. You can buy the hard copy on Amazon if you'd like, but the entire thing is available for free online. The idea here is that he wants to take, as he says here, I wrote a book for non-programmers to provide a friendly introduction to the R language. Okay, so there's really not a scientific concept here, context for how he teaches you, but he walks you through this book about taking beginners through the R programming language. Obviously in a lot more detail than we were able to cover here today, but this is a great place to start if you really want to get some more fundamentals on the R programming language. This is another great book. This is a must-read for any scientist who works with R, from beginners all the way up to advanced users. This is the book called R for Data Science. It was written by Hadley Wickham. He is this huge figure in the R community. He's the author of the ggplot2 package. He's the main architect of the tidyverse and the dplyr packages. Just a really great guy in the community, really interested in helping new users learn about R. And frankly, he's building tools to make it easier to work with data. That's kind of his real focus here. He's written this book along with Garrett, the person that wrote the previous book. This walks you through essentially the data science pipeline, from data visualization with ggplot2 to transforming data, to using dplyr. Lots of the same things that we talked about in our course today in the workshop is covered here in much more detail with lots of examples. I would say it's fairly accessible. It might be a little bit challenging for a complete R beginner, but I think maybe with the foundation that we've gone over today, that you could probably start going through this book, at least to a certain level, and be able to execute the various examples that are present there. So this is a really great book, highly recommended. If you don't read it now, put it on your reading list to read when you're ready for it. Okay, so those are 2 great resources. There's lots of people to follow here. So obviously, Dr. Olga Vitek and her team obviously are doing really great things in mass spec. This May Institute is just one of them with lots of great R packages. So it's great to follow the work that they're doing is really useful. In terms of R packages, specifically more for scientific research, including mass spectrometry, there's a site called Bioconductor. That's where lots of these packages live and breathe. If you search for, say, mass spec here or mass spectrometry or something, you'll get lots of packages coming up, including lots of packages that Olga and her team have been authors of. But there's lots of packages here that could be interesting here for you to work with. So Bioconductor is essentially the repository for scientific packages in the biological and biotech sort of space where you can go to install these packages. So Bioconductor is great to look through. There are lots, if you're more sort of interested on general R, how it's being developed, and some interesting R resources, maybe even outside the field of mass spec. There's new stuff coming on all the time. People are doing interesting things with R. Here's a list of people that you can follow on Twitter. Just noting that a lot of times on Twitter, they don't always necessarily talk about R. You can get all kinds of other topics that may or may not be of interest. But if something interesting in the R community is popping up, one of these people are probably going to tweet about it. There's also Dave Robinson. He's a great R user. I don't think he's doing this anymore, but he was doing things called Tidy Tuesday, where he would take a data set and he would sort of real-time live code his analysis of the data set. And he would write the code and he would talk through what he's doing, and he would make data visualizations and build models and analyze the data. And it was really cool to see somebody like him go and take data sets and work through them and do analyses. I don't think he's doing that anymore actively, but he does have a lot of things on YouTube that you can take a look at. And I think those are really useful to do. He's a great person in the R community to look up. Okay, where to get help? You're undoubtedly going to run into lots of errors and problems. How do we get help? One problem about the R programming language is that R as a thing to search for on Google is not all that great, not all that specific. So one way to help you in your search is if you get error messages, copy and paste them from the output and put quotes around them. You might want to put R in there, or maybe R programming or R code to kind of help Google navigate itself into the hopefully relevant results. But that can help. Also put package names in there. That can help make your R searches a little more relevant on Google. I have to say, over the last couple of years here, it's gotten a lot better. Google's gotten a lot better at searching for these sort of more R specific kind of issues in terms of how it returns search results. Stack Overflow is a place to go. I would use it with caution. A lot of people will go to Stack Overflow and just copy and paste code snippets. I just be a little careful about that. I sometimes see some good examples and some good code there, and I sometimes see stuff that's not so good. So Stack Overflow is a place to go, but just be careful. You can have a mixed bag there. RStudio community is a neat place to go. This is a very R specific sort of message board here. People are sort of required to be very friendly. Any kind of sort of abusive language or derogatory kind of comments and things are not tolerated at all on this site at all. So people can ask lots of questions about R and so on. And this is a great place to go and get some information in a friendly place where people are expected to be nice, particularly to beginners. Maybe not as extensive as Stack Overflow, but it certainly is a resource that's growing up. If you haven't done this, if you're really interested in R, I highly suggest joining in a local R users group. There are R users groups throughout the world, actually. They're growing every day. I help run an R users group in Orange County in California, where I live. And our group has really grown over the last, say, 5+ years. We have, I think, close to 1,000 people, at least on the meetup site, that have signed up, but we have, hundreds of people that show up for some of our events. And it's just a great way to interact with people using R in different contexts. You learn a lot. You'll make great connections. I think it's really useful. So I highly suggest seeking out any local R users groups in your community. I think you will find it will be very worthwhile. Of course, post-COVID and all those kinds of things, most groups are not obviously meeting right now, but something to think about for the future. Okay, need to